can you tell me about constant volume and constant pressure capacities? See, I utilize this one a ton. If I want to calculate delta H, we know delta H is equal to the heat exchange under what conditions? Yep. Okay. What about delta U? If we want to measure delta U, how does that relate to the heat exchange? Constant, what was that? Yep. Okay. How can we calculate those easily with heat capacities? What's this top one going to be equal to? Integral, what else do we got? If I want to incorporate heat capacities. Yep. Perfect. What about for constant volume? What would we do? Yeah. Okay. And we came up with expressions associated with those. Where what we tried to do, or what we did do is we looked at the differential with respect to H differential of U, and then we found change in U versus temperature, right? Okay. There is actually a connection between CP and CV. So if you know CP, you can figure out CV. Why might this be beneficial? It might be beneficial where you're told the delta H, you can figure out your CP, but you know nothing about delta U. You don't have enough information to utilize, let's say, the first law. So how could you find out delta U? Well, if you know CP, the relationship associated with it, you can figure out CV, and you can calculate this and get any property you need. So let's talk about the relationship between CP and CV. Oops, that should be a lowercase or a subscript. There we go. Okay, before we do that, let's do a little refresher because it's been break and no one remembers anything after break, including myself. You had a moment of freedom where you get to relax. Did anyone binge Netflix? Yeah? No? I watched as much Demon Slayer as I possibly could. It was good. What did we say U was a function of last time? Yep, temperature and volume. Do we have to pick those two? No, we did because you guys trusted me. Very trusting of you. If we wanted to split this differential up, what would it be? Partial of U with respect to what?
Temperature.
Sure. What do we keep in constant then?
Volume.
Yep. D what?
Q.
Yep. Plus what else?
Partial of U.
Yep.
Over partial of U.
Yep.
Keeping C constant. CP.
Yeah. Perfect. Okay. And then we have another way to define du. Let's do it up here. Going back to the first law, du is equal to what?
dQ plus dW.
Yep. Okay. We can transform this though if we only look at pressure volume. What does dW become?
Negative dDV.
Yep. Perfect. Okay, and we can set these two equations equal to one another, right? Partial of V, T, V is equal to. And we came to that derivation a couple times, and I said, hey, it's going to be important. What we want to do next is we want to isolate Q on one side. To do that, what would you do?
PD.
Yeah. Get dq is equal to all of this stuff. Okay. Fancy chunks over here. You see any ways to make your life simpler, or can anything be reduced down or simplified?
And take the TV.
Yeah, you can pull out the DV, so this term. Oops. Oh, yeah, there we go. Yeah. Anything else we can simplify? This thing, what's this thing? Some change in internal energy with respect to temperature, keeping volume constant. Yeah, that's CV. Okay. So what we're going to do next is we're going to try to find a connection between CV and CP. What we are going to do at this point is we're going to assume constant pressure, just to make our lives a bit easier to show what's going on. So we're going to assume constant P, basically just to make our lives easier. Find the relationship between CV and CP. Okay. When we do that, does anything actually change in this equation? No, nothing changes, but that P doesn't get varied, it's just a value, P. So we're going to rewrite this, and it seems redundant because it 100% is. What are we looking for again? What are we trying to find?
Relationship between CV and CP.
Yeah. Okay. So let's find a relationship between those two. To do that, let's isolate CV. Put a dot here. CV, not CR. How could we isolate CV by itself? What would you divide through? Yeah. Okay, let's do that. So we get Q, dQ, dt is equal to CV plus this bulky thing We can change this around though because of our conditions. I'm going to change these D's to partials just to keep them like the same symbolic terms that we utilize. What else do I have to imply here?
P is constant.
Yep, P is constant. Okay, what does that mean I have to do to this thing? P is constant. What's that Q gonna become then? Not just regular Q. Yeah. Okay. Whenever you see heat exchange at constant pressure, what should you be thinking in your head? Yep, delta H. That's nice because it's a state function. So if I look at dq sub P, what's that equal to? Not delta H, but dH. Okay. What we're going to do now is we're going to plug this in. Oops, I need yellow now. Plug that guy into here. Why would we want to do that? Why do we want to get rid of Q, basically? Why do we want to be free of Q? What type of function is Q? Yeah, it's path, right? Paths suck because you have to, one, calculate things in a way more difficult fashion. You can't look at initial and final states. You got to consider the history. So, if we plug in that, then we got an H, which is also because it's a state function. So how does this change? It's not dq anymore. What is it? Partial of H over partial of what? P keeping what constant? Yep. And we got CV plus this ugly thing. Okay. Can we simplify this to anything else? Yeah, we can. Okay. Change in enthalpy with respect to temperature keeping pressure constant. What is that thing? That's CP. So now we have a relationship between them. Awesome. But how many people are actually thinking awesome in their head right now? No, one just might be because you don't really care that much about heat capacities, which hurts my soul a little bit. But what's the other reason you're thinking, I don't want to deal with this?
A lot of other variables.
What was that?
There's a lot of other variables.
Yeah, look at all this other bullshit. I don't want to have to deal with that. That's a pain in the ass, right? Okay, I'm here to tell you for most equations of state that we're going to look at, it really isn't. We're going to go through an example with an ideal gas. But you can look at other equations of state where, yeah, it totally is a pain in the ass. You don't want to deal with that thing. So let's look at an ideal gas, and let's see the relationship between CP and CV, and hopefully come to something that's a bit easier to work with rather than forcing you to do this derivative. The nice thing is it actually works out to just be fractions. They're numbers one another. And we'll see that in a minute. So let's erase all this junk, but we're going to utilize this thing, okay? So what's the easiest equation of state to deal with? So what's the easiest one? Yeah, PV equals nRT. I love PV equals nRT. It's the easiest. You've utilized this since Gen Chem. It really doesn't get more difficult, just gets simpler as you go on. So we're going to ask, what is a relationship where CP and CV if the system is an ideal gas? And we're going to utilize this equation. Okay. All right. You told me the equation of state. We don't really know CV or CP yet, but we'll figure out a number for those. What differentials, what two things in here do we really have to find? Can we find P pretty easily? Yeah. What do we really have to worry about? What do we got to find? I'm sorry, what was that? Yeah, we got to find volume. Why are you, that's exactly right, Shannon. Why do we have to find volume? So we're trying to get this thing, right? So we have to have an expression for volume. Okay, manipulate the equation of state around what's volume equal to? Okay. Great. Now we have to find that differential. Okay. Easy differential, you've actually done it like 4 or 5 times already. If I take the derivative with respect to temperature, what's the result? Yeah. Awesome. Okay. Something you might not know yet, you might know if you read your book a lot, but you might not know, we'll explain why it happens. I always love seeing this for an ideal gas. What's that equal to for an ideal gas? Anybody know? It's a numerical value, I'll tell you that. If you had to guess, what would you say? Well, whenever I say that, it usually comes down to 2 answers, right? What are those 2 answers? 0 and 1 most of the time, right? All right, 50-50 shot. What do we think? 0 or 1? How many people say 0? Raise their hands. Okay. What? Maddie is the only one that's going to say 0. Anybody say 1? Raise their hand. Everybody else. Maddie's right. It's 0. Boom. Okay. We'll explain why in a second. But the important point to know for this, you're going to want to keep that in mind because you can utilize it anytime that you see it. Delta U is a constant when delta T is equal to 0 for an ideal gas. We're going to talk about it after we get through this relationship, but you have to use statistical mechanics to find this We'll do a quick and dirty derivation to show that that is in fact true, but you can utilize this a lot. But what do you have to make sure is true about this system in order to do this? What was that? Has to be isothermic, and what other thing? It's got to be an ideal gas. It's got to behave ideally. If it doesn't, this is in fact not zero. Okay. So, our equation then becomes Cp is equal to Cv plus a big fat zero plus P times NR over P. Can we reduce this down or simplify anything? Okay, see head nods, yes. What can we do? Yeah, P is king. So what we're left over with, Cp is equal to Cv plus NR. Okay, this is kind of cool because there are only so many solutions you can get to. There's a definite mathematical relationship where if we manipulate these things over, if we wanted to have NR by itself, it's Cp, what else do we have? Yeah. So there's only so many sets of numbers that will work for this. We don't have to express it, so these are heat capacities, they're not molar heat capacities. If we wanted to express this, what do I mean by, like, what was molar volume again? VM? Yeah, volume over moles. Here, if I want molar heat capacities, we could express it as Cp M, so it'd be Cp divided by N. A faster way to do that is just to put a bar over the top. That way you don't have to write all this junk out. Cv, and what's going to happen here then? Yeah, it's just equal to R. Okay. Cool. So we have a pretty simple relationship here. We know that R is just the ideal gas constant. But how many solutions are there really to this problem right now? What numbers can go here? Really any two numbers that just differ by R, right? You can plug in an infinite amount. It's not really good because we want Cp and Cv just to be a number, right? So let's ask ourselves, what are the values? Cp bar and Cp bar. Or an ideal gas. Okay. We know that's true, right? We said that these guys have to differ by just a factor of R, right? So how could you define Cp and Cv then? What do you think? Or any ideas? these guys could just be some coefficient times r, right? So we could have x times r minus y times r is equal to r, right? That's equal to that, that's equal to that. How could we simplify this pink equation here?
Pull out the R.
Yeah.
And divide by.
That's equal to 1, right? Okay. We could look through and we could solve, we have a bunch of different ones that we could go with. I'm just going to tell you what the answer is. X is equal to 5/2, and y is equal to 3/2. Could have any, there's only so many numbers that would work, but these are the ones that we're going to go with. Why are we going to go with these? Well, they come from the kinetic theories of gases. Which is actually a really cool result, because when you go through the derivation of this, people were looking at heat capacities. They said, this is the smallest ratio that we can figure out. And then later on, Boltzmann, who said everything was made of particles, and people really didn't agree with him. The only way that these numbers fell out was assuming a Boltzmann distribution, that gas particles or gases were made up of tiny particles moving around. So it was confirmation that, hey, kinetic theory of gases, Boltzmann distributions, and the idea that matter was made up of tiny particles was true. So it connected those. It's a pretty aggravating moment for everybody else, because no one liked the idea that things were made of tiny particles. They ostracized Boltzmann for that stuff. So if we look at the values then, CP, what's CP equal to?
5/2 times R.
Yeah. Okay, that's pretty cool, because R is just a constant. We got to multiply it by 5/2. 8, 5, and what do you think the units on that thing are going to be? Or what do we usually pick for R when we want to deal with work or heat exchange and stuff like that? Yeah. And then what about CV? What's its value?
3/2 R.
Yeah. 3/2 R for 12.471 joules per. Okay. All right, the benefit to that is you can utilize this whenever you have an ideal gas. You want to calculate the heat exchange, let's say at constant pressure. Delta H is equal to QP, which is equal to the integral, I don't know, let's P1, P2, CP, dt. If we have an ideal gas, and CP is constant, how is this going to change?
Pull out CP.
Well, I'm sorry, yeah, you can pull out CP, right? And we know the value of CP. What's the value of it?
The 5/2 R.
Yeah, got 5/2 of R times dt. That's awesome, that's easy. Cool, so are there any questions about that? So 2 really cool things to fall out of this. We get these numbers which come from kinetic theory of gases, which helps prove that gases are made of tiny particles that float around. The other thing is we can find a relationship between CP and CV. We came up with an expression for that. So if you ever need to find one for a different equation of state, you should be able to do it. Okay? Any questions? Yeah, Tessa.
So earlier, when we were like deriving like the CP and CV terms,
Yeah.
we assumed ideal gas and isothermic, so why
Yes.
can we do that down here when temperature is changing?
Oh, okay, so, so this term, we had this thing here, right? What was it? dV,
DP, yeah.
T? That thing?
Yeah.
So, our differential is saying we're keeping T constant. That fell out of our expression for du. Oops. Where we had to have that thing split up into this, and then, what was it? du, dt, keeping V constant, right? So that just sort of hung around. When we're talking about an ideal gas, we said this term drops to 0 because if you keep the system isothermal, the change in U is 0. You're asking why, right? Why is that true? That's what I hope to talk about today, but we'll have to talk about next time because we've run out of time. But we're going to discuss that. Actually, I think we can get through it relatively quick. Let's try. It doesn't take much time. Go for it. Okay. So let's talk about the isothermal process. And delta U. What does isothermal mean again? Yep, constant temperature. So delta T is equal to 0. From statistical mechanics, U is equal to 3/2 nRT. For an ideal monoatomic gas. In order to explain where this truly comes from, we have to cover the second law of thermodynamics, which we've only talked about the first, entropy to get there. So you have to trust me here that it just falls out from entropy. We'll try to show that later though, okay? So then, if I look at delta U, it's what minus what always for a delta?
Final minus initial.
Yep, final minus initial. So in this case, we have 3/2 nRTF minus 3/2 nRTI. What could we simplify this to? What was it, Tessa?
3 times nRT delta T.
Yeah.
Nr delta T, yes.
Yep. 0, so our change in internal energy is 0. So if we go back to this differential, we basically have a 0 up top where we're taking the differential of it. That's just going to be a 0 on top. Does that answer your question? I know it's not satisfying because I say, it comes from statistical mechanics, trust me here. I promise you we will get to the point where we actually figure out where does this come from. We just need tools we don't have yet, okay? Is that satisfying enough for now?
Yeah.
Okay. We'll talk more about this stuff next time. Are there any other questions? So know how to utilize that equation where we had the relationship for heat capacities. Big important thing, know this by heart for ideal monoatomic gases. You can utilize it a ton. Any other questions? Okay. Still working through lab reports. Our lab's meant to be due this week. Have them due by the end of the weekend. Does that work for everybody?
What day would that be?
Sunday.
Sounds good.
If they're there Monday afternoon, that's perfect for me, because then I will actually start looking at them. So what happens every year, I go, we'll push it back a little bit, and then I just keep getting behind. As long as it's okay with you guys, I really want to get you feedback back before you turn in your next ones, okay? Does that work with everybody? Okay, can someone tell Ellen that too? Okay, great. All right, I will see everybody later. I'm going to be in Dr. Santos's class for about 15 minutes. I will be out after I conduct an evaluation for her, okay? So if you need me, I'll be around. Okay? All right, have a good day. See you guys later.
Where are you going? Yeah. No, I was gonna go, that's my top.
Also, BChem 2 is being taught next semester at the same time. I know you might want to think about it, but those who are interested, go for it. It's very helpful and important if you're going to go into research. See you guys later.